What specific problem does the NSA method aim to solve in the context of long context modeling for large language models?
The NSA method aims to solve the critical latency bottleneck associated with vanilla attention mechanisms in long context modeling for large language models, particularly as sequence lengths increase. It addresses two key challenges: achieving hardware-aligned inference speedup and enabling training-aware algorithm design. By leveraging the inherent sparsity of softmax attention, NSA reduces per-query computation through hierarchical token modeling, which organizes keys and values into temporal blocks and processes them via three distinct attention paths. This design not only enhances computational efficiency during both training and inference, but also ensures that the model can effectively utilize long-context information without sacrificing performance. Ultimately, NSA seeks to provide a more efficient and effective sparse attention architecture that balances model capability with computational demands.
How does the proposed NSA method work? Illustrate its workings step by step, explaining the role of hierarchy in token modeling.
The proposed natively trainable sparse attention NSA method operates through a hierarchical token modeling approach that enhances both computational efficiency and model performance. First, NSA organizes keys and values into temporal blocks, allowing for three distinct attention paths: compressed coarse-grained tokens, selectively retained fine-grained tokens, and a sliding window for local contextual information. The compressed tokens aggregate information from sequential blocks, reducing computational burden while capturing higher-level semantics. The selective retention mechanism identifies and preserves the most relevant tokens based on importance scores, ensuring that critical fine-grained information is not lost. Finally, the sliding window branch focuses on local context, allowing the model to effectively learn from recent tokens while maintaining a balance between global awareness and local precision, thus enabling stable learning and efficient attention computation across varying sequence lengths.
Can you provide a simple yet illustrative example of how the NSA algorithm handles a long context input, including the steps of token compression, selection, and sliding window?
The NSA algorithm processes long context inputs through a structured approach involving three key steps: token compression, selection, and sliding window. First, during token compression, sequential blocks of keys and values are aggregated into compressed representations, capturing the essential information of entire blocks while reducing computational burden. For instance, if the input sequence is divided into blocks of 32 tokens, each block is transformed into a single compressed key, significantly lowering the number of tokens processed. Next, in the selection phase, the algorithm identifies and retains the most relevant blocks based on their importance scores, which are derived from the attention scores of the compressed tokens. This ensures that only the top-end blocks, which are crucial for the current query, are selected for further processing. Finally, the sliding window mechanism maintains a recent context of tokens, allowing the model to focus on local patterns while processing the selected and compressed tokens. This combination of strategies enables NSA to efficiently manage long context inputs, balancing global awareness with local precision.
What are the theoretical and practical benefits of using NSA over traditional model architectures? Can you quantify any specific improvements in terms of efficiency or performance metrics?
The natively trainable sparse attention NSA architecture offers significant theoretical and practical benefits over traditional model architectures, particularly in handling long context scenarios. Theoretically, NSA reduces per-query computation by organizing keys and values into temporal blocks and employing three attention paths, which allows for efficient processing while maintaining model performance. Practically, NSA achieves substantial speedups, with experimental results indicating up to 9.0 times faster forward and 6.0 times faster backward speed compared to full attention at 64K context lengths. Additionally, NSA outperforms existing sparse attention methods and achieves superior performance metrics, such as A+O, 0.42 improvement on the drop benchmark and A+O, 0.75 increase in accuracy on the AMI 24 benchmark, demonstrating its effectiveness in complex reasoning tasks. Overall, NSA's design effectively balances computational efficiency and model capability, validating its advantages in real-world applications.
How was NSA validated in the experiments? What datasets and metrics were used to demonstrate its effectiveness, and what were the controls in place to ensure a fair comparison?
NSA was validated through comprehensive experiments on real-world language corpora, specifically evaluating its performance across general language benchmarks, long context benchmarks, and chain-of-thought reasoning tasks. The datasets used included MMLU, MMLU Pro, CMMLU, BBH, GSM-8K, Math, DROP, MBPP, and Human Eval for general evaluations, while long context evaluations were conducted using LongBench, ensuring consistent sparsity across all sparse attention methods. For chain-of-thought reasoning, NSA was compared against a full attention baseline using the American Invitational Mathematics Examination, AMY 24 benchmark. To ensure a fair comparison, both NSA and the full attention model were pre-trained on the same 270B tokens of 8K length texts and subsequently fine-tuned on 32K length texts, with both models trained to full convergence. This rigorous setup allowed for a reliable assessment of NSA's performance against established baselines, demonstrating its superior capabilities across various metrics.
Discuss the limitations or drawbacks of the NSA approach. Are there certain types of tasks or data for which it might not perform as well?
The NSA approach, while innovative, has certain limitations that may affect its performance in specific scenarios. One significant drawback is its reliance on blockwise selection and compression strategies, which may not capture fine-grained information effectively in tasks requiring detailed attention to individual tokens, such as nuanced language understanding or tasks with highly variable context importance. Additionally, the architecture's optimization for hardware efficiency could lead to suboptimal performance in environments where memory access patterns are less predictable, potentially hindering its effectiveness in real-time applications with dynamic data. Furthermore, the training-aware design, while beneficial for long-context tasks, may not fully exploit the advantages of sparse attention in shorter sequences, where traditional full attention mechanisms might still outperform NSA. Lastly, the inherent complexity of the hierarchical structure could introduce challenges in tuning and adapting the model for diverse datasets, particularly those that do not exhibit the spatial continuity of attention scores that NSA is designed to leverage.